The following program is brought to you by Caltech.
Well, it's a great pleasure to introduce Jeff Scargle from NASA Ames. Jeff is actually a Caltech product. Welcome back. And he's a world-renowned authority on the analysis of astrophysical time series. His scientific interests are many, mostly in the analysis of high-energy astrophysics data. And he's highly accomplished in the algorithms arena, even has algorithms named after him. Right? Jeff is also a Keck Institute Distinguished Visiting Scholar for this workshop. And the official wording on that is, the Keck Institute Distinguished Visiting Scholars will play a key role there in the activities of the Institute. And so we hope to see Jeff a lot more for the next several months. And now he will deliver his keynote talk.
Thank you very much, George, and the rest of the committee. It's indeed a great honor to come back to Caltech. In fact, you'll see sort of a circle of things that kind of amaze me, that my work here as a graduate student has kind of come back to haunt me in terms of the Crab Nebula, which you heard about a little bit already. I'm going to try to cover a few topics in the general area of time series analysis, and I'm going to start with a kind of abstract representation of what I mean by time series, which may seem kind of silly, but the goal is to try to unify different data modes and to generate algorithms and software that can take input data kind of in a generic form and do all kinds of things with it. I'll talk a little bit about time series models and try to emphasize time domain analysis, because I think that ties in most directly with the workshop. And if time allows, I'll get into some new frequency domain and time scale and time frequency distributions, which I think are going to be very useful in the future. So here's a picture of something I call a data cell, and it's kind of what you're maybe do anyway, but it's a bit abstract. That is, it represents a measurement, and it includes any information that's relevant to whatever algorithm you're going to use on the data. Maybe some intensity as a function of time. You need to know what time the measurement was made at. Maybe you need the energy of a photon. But the point of the abstraction is that it can represent any kind of measurement. For example, in high energy astronomy, often what you have is a sequence of photon detection times, and so the raw data is a time of detection. In radio astronomy, you measure a flux as a function at a given time. Sometimes in high energy, you have something called a time to spill data mode, which is how long it takes some buffer to fill up on the spacecraft. But the point is that some of the algorithms that I'm going to talk about later can accept data in any of those forms, and in fact, any mixture of those forms. You could have different data cells, as long as they have the right information in them, mix and match and dump them into an algorithm, and everything works out fine. A time series then is nothing but a sequence of these data cells ordered in time, and that's really all there is to it. That's the input for some analysis technique. And let me give an example of the photon detection time that I talked about. What the cell for a sequence of photons, these red dots represent successive photon times in a high energy detector. What you can do is construct a cell that visually and geometrically is a rectangle extending from the midpoint between the photon you're interested in and the previous one and the midpoint, the successive one. It's kind of a one-dimensional Voronoi tessellation, if you will, and have the height of that cell be 1 divided by this time interval. And in fact, it turns out you can then calculate things like autocorrelation and cross-correlation functions by treating the height of this rectangle as the measured variable. And you can even adjust for exposure and by shrinking the cell according to the value of the relative exposure. And it turns out that gaps are very easy to treat with this point of view. Okay, let's move on to models of time series, because that's where the physics comes in. I still remember that maybe it wasn't one day, but when I was a graduate student here, wondering why it is that the only thing astronomers could do with time series data was take a Fourier transform and make a power spectrum out of it. There was nothing beyond that in a sense, even though a lot of statistical methods and a lot of time series methods were developed initially in astronomy by Gauss and Schuster and early people, but a lot of astronomers didn't know anything about it. So I went across to Millikan Library and remember discovering this theorem in a books on economics. It's called the Wold decomposition theorem. Here's a picture of the inventor of it, an econometrician. And it's a very interesting theorem that has a lot of ramifications, and I could spend all morning talking about it. But for astronomy, what it really is a representation proof that any stationary process can be represented in this very simple way as the sum of two parts, one of which is completely deterministic, and in the blue part, and the red part is completely random. And in turn, the random part has a very special form, something called a moving average, not to be confused with a running mean type of moving average, but it's a general representation of random processes where in terms of like an electrical engineering analog, it's white noise, R of T, it's a white noise process run through a filter. And astrophysically, that filter represents the shape of some flare process or some outburst in the random variability of the source. And one of the amazing things about this theorem is, first of all, how general it is. Any stationary process has this representation. But the representation is very special. In addition to being of this form, this pulse shape or flare shape has a bunch of properties which are quite restrictive. And one of the interesting things is to understand how it is that a physical process that, for example, doesn't have a constant flare shape, how is that possibly represented mathematically as a process that does have a constant flare shape? I still haven't quite understood that, but anyway, I think this should be regarded as a very important, as I say, existence proof for astrophysical models. What about this stationarity condition? That word gets tossed around quite a bit. In a way, it's a very difficult thing to deal with in practice because the formal definitions that you see in the textbooks only apply if you have an infinite amount of data, so to speak. They're limiting definitions. So a lot of thought has been put into this by statisticians and mathematicians. Flandrin and Dave Donahoe at Stanford and others have developed notions implementing the concept that stationarity is kind of really a local, the only thing you can really deal with in practice is a local concept. And anybody who's interested in this, I think this paper by Patrick Flandrin and other co-authors has a very nice approach. And I like their discussion of this in a two-dimensional context. This set of pictures of the same location on the Earth at different scales kind of shows visually the kind of concept. The idea is here you start off with you're very high up and you see a lot of inhomogeneities. This is not a stationary process statistically. There are broad regions where there's water, I guess, and land, and you wouldn't call this a sort of a uniform thing. But on a different scale, as you move in, you see a fairly uniform or stationary spatial distribution because you're looking at sort of a city that's laid out in some reasonable way. But if you zoom in again, you see a lot of substructure, and zoom in again, and sort of cheating, you pick an area that looks kind of smooth. So it's clear that not only is stationarity a local property, but it depends a lot on the scale, and you can go back and forth from a stationary to a non-stationary process. And of course, the same concepts apply in one-dimensional time, but I think it's nice to see this in a more graphical way. And here's kind of in a way, it's sort of a sobering picture for astronomers, because what's going on when you observe variable sources is not simple. There are several random processes going on that you have to deal with. One is that the luminosity of the original source may be random or deterministic. It may be fluctuating as variable sources. But in addition, there's a completely separate random process that is the emission of photons. You can sort of think of this as almost a quantum mechanical random emission process. And then things are not necessarily smooth along the way to the Earth. There's random effects that can affect the signal depending on the wavelength as it comes to the Earth. And then there's another random process going on, that is the photon detection. You can think of the radiant flux at the detector as a probability, and you're sampling from that in kind of a Poisson process way. And so this is a bit complicated, but I stress this because in the literature you'll see a lot of confusion between these processes, and statements made that correlation here implies that you cannot do certain things here because the data are not uncorrelated. And that's not true at all of this photon detection process. This is completely an uncorrelated or independent process, even if there's strong correlations here. Okay, let's now focus, like I said, on the closest thing to what we're going to be talking about in the workshop the rest of the week, I believe, is the time domain. And there's an algorithm that I've developed for time domain modeling of time series in general in astronomy that is kind of the simplest possible model you could make of a variable source is a piecewise constant or step function model, so to speak, of the time series. And this is now being used quite a bit in various, especially high energy sources, high energy missions, under the name of Bayesian blocks. And I'm a little bit embarrassed that I now think it probably is misnamed and should be called maximum likelihood blocks, because they're the fitness function that turns out to be more practical for applying the method is more like a maximum likelihood thing than a Bayesian posterior. But anyway, it's a segmentation approach, and it's like I say, it's basically a step function representation of the time series. It's non-parametric in the usual sort of backward sense, namely has many parameters. That is, it's not fitting a parametric model to the data, but it has a lot of generic parameters that allow you to fit a signal of any shape. And there are few assumptions on it. The only thing you need to assume, so to speak, are sort of generic prior distributions on the amplitudes of the blocks or elements of the signal, and the number, you need a prior on the number of blocks. But the key thing is that it does not impose any resolution or limitation on the resolution of the analysis method at all. For example, it's not like taking photon event data and putting it in bins and looking at a histogram, so to speak, where you have to pick the bins. In addition, the algorithm is, I can say it's very clever because I didn't actually develop the mathematics behind it myself. I was working with Brad Jackson, a mathematician at San Jose State. It's a very clever algorithm, and it even has a very simple mode that you can switch on where it finds the first significant, in sort of a time-ordered way, it finds the first significant time that a signal rises above a statistical background. But it's more often used for retrospective analysis of event data or other kinds of data. And even though the representation is discontinuous, it's like I say, a step function, and in some sense, it's not a very pretty way to represent a time series. It's very convenient for further analysis. If you want to calculate something like a rise time of a flare or the duration of a gamma ray burst or something, the step function representation is very convenient for calculating things like that. On the other hand, it's not good. It's not meant to detect global structure in the time series like periodicities or quasi-periodicities. It's meant to exhibit local structure in time. And it's currently an n-squared algorithm, but it can probably be sped up. Well, enough about exactly how great it is, so to speak, but it's based on this concept of taking a sequence of these data cells and breaking them into blocks and trying to fit a constant model to each of the blocks, so to speak. And here's just a graphical way that the sequence of cells are divided into blocks. And here, I probably shouldn't show this because it makes the algorithm seem so simple. It's a few lines of MATLAB code, but it's really leveraging a very interesting approach to this kind of analysis called dynamic programming. The idea behind this actually goes back to work by Richard Bellman in the 1950s. It's an algorithm that works iteratively. It starts with the first data point and then adds one data point at each time. That's why it's n-squared, but that's also why this real-time trigger mode can work. You can kind of stop the first time you detect a change point. Change point is just the technical term for the time at which one block ends and the next block begins. Well, it's probably easier to see what's going on in terms of a picture. This is some data, I think, from a gamma ray burst. I forget exactly where I got this, and so the yellow histogram is just a binned histogram of the times of the individual events. The raw data, of course, are not binned in this way. The raw data are just a sequence of times. But in order to see what's going on at all, you kind of have to do some binning. The blue plot is the Bayesian block, or in this case, a maximum likelihood block representation of the raw data. That you can see, of course, is kind of like binning the data with variable bin sizes, where not only the sizes of the bins are determined by the data, but their locations are determined by the data. So again, you haven't imposed anything on the resolution. Like here's a very sharp rise, a pulse in the gamma ray burst, that if you had a broader bin, for example, the yellow binning doesn't particularly show that event. So it's a very simple idea. As I say, I think it's the simplest conceivable model of a variable source that isn't completely trivial. And here's the kind of an amazing recent discovery. This is some data from the Fermi Gamma Ray Telescope of the Crab Nebula, the flux from the Crab Nebula, which for many years has been used as a standard candle because it was known that it couldn't vary. Well, actually, my thesis back here many years ago at Caltech was called Activity in the Crab Nebula, and it was clear there was stuff going on from optical observations of the crab, and the synchrotron plasma is not a quiet and serene thing. It's being stirred up by the pulsar, and in a way it's not too surprising that there is variability, but these sharp flares, these kind of dramatic increases in the flux, the gamma ray flux. This is, by the way, it's a very broad band extending up to over a GeV in energy, but most of the flux is in the hundreds of MeV range. So anyway, here's a Bayesian block representation of this same data, the raw data that went into generating this curve. And you see what it says is that there's, most of the time it's fairly constant, but in fact there are flares that you can see with your eye. You can see these events here, but what this analysis suggests is, and by the way, this lower panel is just a blow up of this interesting region of the bright flare, showing, again, there's no defined time resolution, so there's 3 pulses within this flare that are distinct and separated, and independent work by other people confirm that viewpoint, that's real. But the suggestion is that, that these flares are kind of part of a continuing random variability, and they're sort of just the high end of a distribution function for amplitudes of flaring events. And so, in a sense, these events shouldn't be called individual flares. It's a continuing random kind of bubbling activity. And by the way, the number of possible ways of segmenting this kind of data is essentially 2 to the n, where n is the number of data points. Of course, that's a huge number. It's an exponential number. And for this particular data, the number of possible segmentations of 15,000 some photons is 10 to the 468. This algorithm actually finds, it doesn't explicitly search that entire space, obviously, but it does, it's guaranteed to find the global optimum over that space because of this trick of dynamic programming. And it really works very, very well in practice. There is the kind of main limitation is there is one free parameter. I think any algorithm like this always has some kind of parameter to kind of adjust or modify some notion of smoothness. In this case, it's I mentioned a prior on the number of blocks or the number of change points. It's sort of, it's not really a smoothing parameter because you never smooth out, you never lose these sharp edges. You never get rid of signals because of rounding edges or smoothing out the data. But by modulating this prior probability of the number of change points, you can find that there are fewer details shown in the representation. So in effect, it is a kind of quasi-smoothing parameter. And recently, some colleagues working with me on this at SLAC and other places, we've worked out some ways of figuring out what the best value for that prior parameter is. And so it's become less of a worry what the choice of that parameter is. And I think here's just to show you the algorithm being used in a lot of different Fermi data. And this shows another mode, another data mode, where the raw, this is kind of a mixture. This is a mixture of event data, and then some, the red points with error bars are this other data mode where you have a measurement and some uncertainty estimate assumed to be normal, showing that you can mix those together. And you can see that the gaps are, this is an actual gap in the data, and often one block ends at before the gap, and then the next block begins after the gap. But it's possible for a block to span a gap because the rate before and after that interruption are statistically the same, and you get a better model if you assume that that's a single event rate going across that whole interval. Of course, the algorithm isn't saying anything about what's really happening in the gap. It's just saying that it's sort of a consistency with the data, but in other cases, but in any case, you're never magically interpolating into the gap. That should be obvious. And here's some radio data. This is actually from the Owens Valley survey that some people here at Caltech are part of, showing this mode where you don't have individual photon events, but you have normally distributed data with a lot of, so in some cases, large intervals between the points. Okay, this is a bit of a tangent, but if you think about it, for the event mode, what I've just been talking about as a time series analysis method is nothing other than a histogram of the arrival times. And here's some data. It happens to be the fluxes of the Crab Nebula from the previous plot, but you can think of them as any kind of a data source. And here, it's the same data with histograms, ordinary histograms, calculated with different bin sizes. And I've just indicated the number of bins, 16, 32, 64, and 128, showing that, of course, what you see depends a lot on your choice of the sizes of the bins. And what's the right thing? Is this showing noise? And this is a better representation of the real distribution. Is this the best one because it's smoothness? And that's always a problem. So I have an algorithm which is essentially a general purpose histogrammer that doesn't make any assumption about the sizes of the bins or even their locations, and doesn't even make them be equal. The bins are determined by the data. And here's what happened when I ran it on this data. Here's the histogram I got, a fairly smooth one, but there was one bin that was really high. And first I have to admit, I thought, well, something's gone wrong with the algorithm. That looks strange. But what you see, the blue histogram is where I cranked up the number of bins, and sure enough, there is if you make the binning fine enough, you would have discovered this event. And here's a blow up at the center. This blue bin is from an ordinary evenly spaced histogram. But I think you wouldn't have necessarily seen that if you had just looked at this and said, well, I've kind of covered the waterfront, and there's nothing really going on at very fine resolution, so to speak. But in fact, this is a real, and it turns out unfortunately it's not a signature of something going on in the Crab Nebula. It happens that this is preliminary data with the Fermi data analysis is a bit complicated, and there's an iterative fitting thing with the starting value. And it happened that this pileup is kind of an artifact of a starting value that's at the location of this black line. So that in a way, this is an artifact, but it's something that I uncovered without knowing about it, just by trusting that Bayesian blocks was doing the right thing. And by the way, in addition to ordinary histograms being dependent on how big you make the bins, it also depends on where the bin edges are located. And the cyan curve represents the peak of an ordinary evenly spaced histogram with the same spacing as shown in dark blue, but with simply shifting the location of the bin edges by from beginning to end. This is one full bin width. And so you see that the actual peak you would get depends on where you pick the edges, not in addition to how big you make the bins. So what I'm trying to sell, I'm trying to encourage everybody to give up ordinary evenly spaced binning that you use and do this very simple thing. And computationally, it's obviously a little bit more complicated than just putting points in bins, but it's not that expensive computationally for most data sets. Okay, and still staying in the time domain, this algorithm is from a fairly old paper now by Edelson and Krolik. This is the title of the paper. It's a fairly well-known algorithm in astronomy, but I recently discovered how really great it is and how generally useful it is. In particular, it's easy to code it up for the very general data mode that I talked about, this very abstract thing at the beginning where I talked about data cells that could be, 2 minutes, could be anything. And here's a cartoon of how it works, and I don't have time to go into details, but it's a very simple idea. Here's the ordinary auto or cross correlation function where you take points separated by a given lag. The generalization is instead of you kind of collect together all points that happen to lie within some lag interval instead of at a precisely defined lag. Here's an example of an autocorrelation from some MAXI data of Japanese X-ray experiment on the space station. And again, I don't have time to go into details, but you can get error estimates and so on from data. Here's some X-ray data from ASCA with incredible sampling in a sense. There's all kinds of gaps due to the orbital motion of the spacecraft and interruptions. And in general, you think you'd really have a hard time getting an autocorrelation function. But here I represent each photon with one of those shells. The red dots are those 1 over delta T cells. Plug that into and there's a blow up showing you how big the gaps are and so on. Anyway, you get a fairly clean autocorrelation function just by, sorry, does that mean I'm over time? Okay, sorry. Okay, well, and just as an aside, this whole scheme works in higher dimensions, so you have to generate a fitness function that's appropriate to higher dimensions, but this using Voronoi cells. And here's an example of this is not a very good representation of a 3D Bayesian block analysis of the structure in the Sloan Digital Sky Survey, getting kind of a density estimate of the distribution of galaxies in the universe. So I have a few more things, but I think this is a good time to stop. Thanks very much.